Hey guys, and welcome back to my channel. Today I'm going to be doing a COMSOL analysis tutorial on mass transport analysis of a high temperature hydrogen fuel cell. So in addition to COMSOL multiphysics, and I'm using version 6.0 if you're following along, we will be using the fuel cell and electrolyzer module. Jump right in to the background. So first, an introduction to PEMs, PEM. Generally, PEM stands for proton exchange membrane. You might also see that it stands for polymer electrolyte membrane because the membrane itself is a polymer, but proton exchange is a little more specific to the mechanism that's actually allowing the conductivity to happen. A high temperature PEM based on phosphoric acid doped polymer membranes typically operates in a temperature window between 100 and 200 degrees Celsius. Water is produced on the cathode side due to the electrochemical reactions, but water may also be present on the anode side if the fuel stream contains water. The latter may be the case if the hydrogen fuel stems from reforming of hydrocarbon fuels such as natural gas, alcohols, or diesel. So if you were talking about a vehicle, a hydrogen fuel cell vehicle, obviously that would be pure hydrogen from pressurized hydrogen at a refueling station. But if this were, say, on a larger scale, the hydrogen could be sourced from steam, from, as they say, reforming process. So it wouldn't be pure, and then you'd have water and hydrogen introduced on the anode side. Water buildup in the cell results in lower partial pressures of hydrogen and oxygen on the anode and cathode respectively, and thereby also lowers the rate of cell reactions. So basically, if you have an excess of the reagent, hydrogen on one side, then your reaction is just limited by how fast the reaction can go, the reaction rate itself. But if it's limited by the availability of the reagent, hydrogen, then it's going to lower the cell reaction because now the limiting factor is mass transport, not the reaction rate. Okay, so the local water concentration in the cell may have a beneficial impact on the ion conductivity of the membrane. But if water condenses in the cell, it may result in leaching of phosphoric acid out from the polymer matrix, irreversibly reducing the ion conducting capabilities of the membrane and the performance of the whole cell. So during normal operation above 100 degrees Celsius, water normally does not condensate in the cell. But knowledge about the water content in the porous electrodes during operation may also be desired in order to optimize shutdown procedures, since water may condensate when temperature is lowered below 100 degrees. This model example investigates the steady state transport of reactants and water in a cell, including both anode and cathode mass and momentum transport phenomena and the flow channels, gas diffusion layers or GDLs, gas diffusion electrodes, GDEs, as well as electrochemical currents and the GDLs, GDEs, and polymer membrane. Okay, so here is our geometry of the fuel cell. So you've got the membrane in the center, and then GDEs sandwiching the membrane, and GDLs, the gas diffusion layers outside of that, and then the bulk flow on either side. So on the anode side, we'll have the fuel, in this case hydrogen, and on the cathode side, the oxygen. Okay, so the first part is the electrochemical currents theory. In the gas diffusion electrodes, the local current densities depend on the ionic and electronic potentials, but also on local reactant concentrations. On the anode, hydrogen oxidation occurs according to one molecule of diatomic hydrogen breaking up into 2 protons and 2 electrons. No water molecules are assumed to be involved in the proton transport. And the local current density expression is used for the hydrogen oxidation reaction. The cathode, oxygen reacts together with the protons to form water according to this reaction, 1 molecule of diatomic oxygen plus 4 protons plus 4 electrons gives you 2 water molecules. And the following current density expression is used for the oxygen reduction reaction. And this, of course, is just based on rate law. So this is squared because we have 2 molecules of the product. So this partial pressure becomes squared. And here the partial pressure of oxygen is to the power of 1. So we have products minus reactants terms. Anode gas diffusion layer boundaries facing the flow pattern ribs are set to 0 electronic potential, and the corresponding boundaries at the cathode side are set to the cell potential. All other external boundaries are electrically isolated. Moving on to the mass transfer theory. The hydrogen fuel cells interface also solves for the species mass fractions and the flow channels, the GDLs and GDEs, using the Maxwell-Stefan equations. Note that hydrogen and water species are present on the anode side, whereas oxygen, water, and nitrogen are present on the cathode side. Okay, so mole fractions are specified at inlets, and outlet conditions are used at the channel outlets. All other external boundaries use zero flux conditions. And finally, for momentum transfer, our variables U, the velocity vector, and P, pressure, are modeled by the compressible Navier-Stokes equation in the flow channels and by the Brinkman equation in the gas diffusion layers and gas diffusion electrodes by using 2 free and porous media flow interfaces. Couplings for the density, viscosity, velocity, pressure, and net mass sources and sinks are made to the hydrogen fuel cell interface by using reacting flow, hydrogen gas phase and reacting flow, and oxygen gas phase multiphysics notes. At the flow channel inlet boundaries, laminar inlet flow velocity profiles are specified, whereas the pressure is specified at the flow channel outlet boundaries. To model a multiple parallel channel configuration, symmetry boundary conditions are applied along the long sides of the GDLs and GDEs. All other wall conditions use no slip conditions. And this comes from 3-dimensional modeling and experimental study of a high-temperature PBI-based PEM fuel cell published by Ubong, Shi, and Wang in Journal of Electrochemical Society. New Model Wizard. This is going to be a 3D model. And for our physics, we're going to select electrochemistry, hydrogen fuel cells, and this is a proton exchange fuel cell. First one. Click add, and then we're also going to add from the physics selection tree fluid flow. So going back to the top, right under electrochemistry, fluid flow, porous, media, and surface flow, and then FP, which is the bottom, free and porous media flow. And for velocity field, before we move on, let's put UA for the velocity field, and for the velocity field components, we'll have UA, VA, and WA. And for pressure, we'll have PA, indicating this is at the anode side. Add one more free and porous media flow for the cathode side, and this time we'll call the velocity field UC, and each of the components UC, VC, and WC, and the pressure field will be called PC. All right, now we're ready to go to study. And we're going to choose from preset studies for selected physics interfaces, expand hydrogen fuel cell, and choose stationary with initialization. Click done. Now we're ready to load the parameters. So I'll go to in the settings window for parameters under global definitions. We're going to go to load from file and upload the text file, which contains all of the fuel cell parameters. So we've got the cell length is 2 centimeters long, 1 millimeter high. We've got a rib width, the GDL width, porous electrolyte, membrane thickness, electrode thickness, GDL gas pore volume fraction, porosity of the gas GDL, the porosity catalyst layer, the ionomer volume fraction, the catalyst layer gas pore volume fraction, GDL permeability, catalyst layer permeability, conductivity of the GDL, conductivity of the membrane, cell temperature, reference pressure, cell voltage, the reference current densities for cathode and anode, transfer coefficient for the cathode, and inlet conditions for water, hydrogen, and oxygen. We've also got stoichiometry variable or parameters here, and inlet velocity for both fuel sources. So you can get these from the link in the description of this video. All right, now we've got all our parameters. We're going to start on geometry. We've got to draw the channels, gas diffusion layers, porous gas diffusion electrodes, and membrane using rectangular blocks. So this will be a pretty simple geometry. So we'll go to the top tab for geometry and click block. And then in the settings window for width, we're going to type WCH. Oh, and then for the label, we're going to change this to anode channel. Okay, the depth is going to be the length, L. Height is going to be H, CH, height of the channel. And for the position, we're going to position it at, the corner's going to be positioned at X equals W width of the rib over 2. And then in this section at the bottom, selections of resulting entities, we're going to check the box that says resulting object selection, show in physics with domain selection. And then we'll click build selected. And here is our anode channel. So this is the bottom of the entire shape. Now we're gonna move up the sandwich and build the anode GDL next. So we're gonna right click anode channel and click duplicate. And then in the settings window for block, we'll call this one anode GDL. And for the width, it's gonna be width of the channel plus width of the rib. And the height is going to be height GDL. Position is going to be cornered at the origin, and the Z coordinate height of the channel. Build selected. So there's our gas diffusion layer, anode gas diffusion electrode. Right click anode GDL and choose duplicate. We're going to call this anode GDE. Now the size and shape is going to have height of the electrode, same width and depth, and it's going to be positioned at 0, 0, height CH plus height GDL. Build selected. And then if we zoom in, you can see another very thin layer on top of the GDE or GDL. Next is the membrane. So we're gonna copy GDE into a new block and label this one membrane. This one's gonna have the height of the membrane with the same width and depth, and it'll be centered at 0, 0, height of the channel plus height of the GDL plus, you guessed it, height of the electrode. I'm just moving up the sandwich here. Build selected. There's our membrane. Okay, next I'm going to copy anode GDE, or duplicate, and label it cathode GDE. And it's going to have the same width, depth, and height as the other GDE. And we'll go through similar exercise for cathode GDE and cathode GDL. Alright, and I'll hit the zoom extents, and now we can see our entire geometry here. Next, we're going to create some definitions. So we're going to create some explicit definitions for anode inlet, cathode inlet, anode outlets, cathode outlet, and anode and cathode compartments. So we don't have to click on each individual boundary or domain every time we go to select it later on. It'll just kind of speed things up. So first, for anode inlet, we're going to go to the definitions toolbar and click explicit, which is in this third grouping here at the top. And in the settings, we're going to call this anode inlet. And we're going to change the geometric entity level to boundary and select boundary 23 only. Or you can just go to paste and type it in since it's given. Obviously, if this were in tutorial form and you were building this, you wouldn't know what the number is. You'd have to select it, but I'm just using the paste option because it will speed things up. Okay, now we're going to click explicit again, label this one cathode inlet, and this will be boundary 27 only. Oh, boundary 27 only. Explicit again, anode outlets, boundary 30, and cathode outlet, boundary 31. Anode compartment is going to be a union, so we're going to go to definitions toolbar and click union, which is 2 icons over from explicit. We're going to label this anode compartment. Locate the input entity section and under selections to add, click the plus button at the bottom to add selection. So we're going to choose anode channel, anode GDL, anode GDE. Okay. And we'll do the same thing for cathode compartment. Add selections and choose GDE, GDL, and channel. Okay, so this will make our selections in the physics module go much faster. Now we're ready for free and porous media flow for the anode. Set up the domains applicable for the flow interfaces. In the Model Builder window, under Component 1, click Free and Porous Media 1. So this is the second physics module in the Model Builder window. And then we're going to change this label to Free and Porous Media Flow -anode. And for free and porous media flow to We'll just add a cathode in the label to make that more clear. And then for each of those, we're going to locate the domain selection, and from the selection list, choose the appropriate selection. So for the first one, we're going to select So for FP1, on the anode side, we're going to choose anode compartment from the domain selection. And for the FP2 cathode domain, we'll select cathode compartment. All right, now we're ready for multiphysics. Next, couple the interfaces appropriately using the reacting flow multiphysics coupling nodes. Note that currently the multiphysics nodes may not be applicable to any domain selections, but the selections will automatically be updated when the hydrogen fuel cell interface is set up. So first we're going to go to physics, multiphysics couplings, reacting flow hydrogen gas phase, and then choose the other one, oxygen gas phase, RFO1. Now in the settings window for reacting flow O2 gas phase, we're going to locate the coupled interfaces section, and from the fluid flow list, choose FP2 cathode. So to do the actual mass transport analysis, next we're going to set up the current distribution and mass transport model. The default gas species are hydrogen and water on the anode side, and oxygen, nitrogen, and water on the cathode side. Start with adding the relevant domain nodes. So in the model builder window under component 1, we'll click hydrogen fuel cell, and in the physics toolbar, click domains and choose membrane. So you'll see this adds a node under the hydrogen fuel cell grouping in the model builder window. We'll select membrane. Now we're going to add another domain from domains dropdown under hydrogen fuel cell, selecting hydrogen gas diffusion electrode. And then we have to select the domain where this applies. So we're going to go to the drop-down list and choose anode GDE. So the gas diffusion electrode, this node is going to be responsible for the current distribution initialization within the gas diffusion electrode for the anode side. Hydrogen gas diffusion layer, I want to select anode GDL. Now we're going to go to domains and choose hydrogen gas flow channel. Hydrogen gas flow channel, we will choose anode channel. All right, next we're going to add the oxygen gas diffusion electrode. So we'll go to domains and choose oxygen gas diffusion electrode right here. And from the selection list, choose cathode GDE. Now we need to add the domain for oxygen gas diffusion layer, O2 gas diffusion layer, cathode GDL. Oxygen gas flow channel, and from the domain selection, choose cathode channel. All right, on to electrolyte phase setup. Set up the electrolyte conductivity and the electrolyte phase node. Note that in the hydrogen gas phase and oxygen gas phase nodes, the settings are either the default option or automatically set by the multiphysics coupling nodes. In the model builder window, click electrolyte phase 1. From the sigma list, we're going to change this to user defined, type sigma M. Then for hydrogen gas diffusion electrode 1, hydrogen gas, set up the properties of the hydrogen gas diffusion electrode node. The details of electrode kinetics are set in the child node. Note that the reference equilibrium potential is calculated automatically when the default built-in option is used. All right, so in the model builder window, we're going to highlight or click on hydrogen gas diffusion electrode 1, and in the settings window, locate the electrode charge transport section. Now in the sigma S section, we'll type in sigma Gdl, call our parameter Gdl. Okay, and then under the effective electrolyte charge transport section, right underneath it, and the epsilon 1 field, type eps underscore L underscore CL. And in the last section, gas transport, we're going to type epsilon gas CL in epsilon gas section. Okay, so in the model builder window, click hydrogen gas diffusion electrode reaction 1. In the settings window for hydrogen gas diffusion electrode reaction, locate the electrode kinetic section, which is all the way at the bottom. In the reference current, initial reference current text field, we're going to type IO ref sub A. Locate the active species surface area section, and in the A sub V text field, type AV. Moving on to the hydrogen gas diffusion layer, I'm going to set up these properties. So in the model builder window under component 1, hydrogen fuel cell, click hydrogen gas diffusion layer 1. And in the settings, we'll go to electrode charge transport and type sigma Gdl in the sigma S section, sigma Gdl. And under gas transport, we'll put under epsilon section EPS sub gas sub Gdl. Oxygen gas diffusion electrode node is next. The details of the electrode kinetics are set in the child node. Note that the reference equilibrium potential is calculated automatically when the default built-in option is used. All right, so we're going to go to oxygen gas diffusion electrode 1. And in the settings section, locate the electrode charge transport section. Again, for sigma, we're gonna reference sigma Gdl. And under the effective electrolyte charge transport section. All right, so for electrolyte volume fraction, we'll use parameter EPS LCL, and for effective diffusivity correction, we'll use parameter EPS gas CL. Now we're going to go in the model builder window and click on O2 gas diffusion electrode reaction 1, the subnode of O2 gas diffusion electrode. Locate the electrode kinetic section, so you have to scroll down a little bit, go to the reference current function of temperature section, and we're going to use parameter IO sub ref sub I0 sub ref sub C, and in alpha A, the anodic transfer coefficient, we're going to type 4 minus alpha sub C. And it does give you your equations here. So this was given in the background. The rate law derived current density expression, and alpha C equals N minus alpha A. So now we're going to set up the properties of the oxygen gas diffusion layer node. In the settings window for O2 gas diffusion layer, locate electrode charge transport section, and in sigma S, I'm going to type sigma Gdl. So all the gas diffusion layers have the same conductivity and gas pore volume fractions. So for gas transport in the epsilon text field, the pore volume fraction text field will type parameter EPS gas Gdl. There are no settings required on the flow channel nodes other than the domain selection. So next we're ready to set up the boundary conditions and initial values. starting with electronic conducting phase 1. In the physics toolbar, click Attributes, which is the little barrel with a gear icon, and choose Electric Ground. So we're adding a boundary condition here. Select boundaries 3 and 33. So I'm just going to type those in the paste section. 3 and 33, and if we look at the bottom here, this is the bottom surface of the anodic, the ionomer gas diffusion layer. Next, in the Model Builder window, click Electronic Conducting Phase 1. And in the Physics toolbar, again, we're going to click Attributes and choose Electric Potential, adding another boundary condition. And for the boundaries, we'll type in 16 and 35. In the settings window for electric potential, locate the electric potential section. For phi celled S boundary, we're going to type V cell. In the Model Builder window, expand component 1 hydrogen fuel cell, hydrogen gas phase 1 node. And initial values. For initial composition, we're going to change the mixture specification to humidified mixture. And in the temperature of humidification, we're going to type T hum. Next, going to hydrogen gas phase 1. I'm going to click on Attributes and choose Hydrogen Inlet. And from the boundary selection list, choose Anode Inlet. And now we're going to go to gas phase 1 and add an outlet. So attributes, hydrogen outlet, and boundary selection, anode outlet. That'll highlight the other side. And then we'll define the initial values for the hydrogen fuel cell oxygen gas phase. So under oxygen, expanding the oxygen gas phase 1 node, we'll highlight or click on initial values, change the mixture specification to humidified mixture, humidified air. For temperature, change this to T underscore Q. In the Model Builder window, click O2 gas phase 1. Click on Attributes. We're going to choose an oxygen inlet. And from the boundary selection, choose cathode inlet. And then click on O2 gas phase again, Attributes, O2 outlet, and choose cathode outlet. Now we're ready to set up the fluid flow model on the anode side. And click on Free and Porous Media Flow for the anode, FP1. In the settings window for free and porous media flow, locate the physical model section. From the compressibility list, choose compressible flow, meaning the Mach number is less than 0.3. Define the pressure reference level and the interface properties. In the PREF text field, type PREF. So you might be thinking, why did we overwrite 1 atmosphere with PREF when the reference pressure is 1 atmosphere? And we don't need to, but if you wanted to change the operating conditions, it would be much simpler to just jump into parameters and go change your conditions here than to have to remember everywhere the reference pressure was noted in all of your physics modules. All right, picking up where I left off, I was at porous medium 1. So now we're going to set up the channels of the porous gas diffusion electrode gas diffusion layer and the flow channel. Note that the density and viscosity of the gas mixture are calculated by the hydrogen fuel cell interface and automatically set by the multiphysics coupling nodes. Alright, so from porous media, for porous medium 1, we're going to go to the physics toolbar, click domains, and choose porous medium, which is the anode Gdl. So from the domain selection, we're going to go to the drop-down menu and select anode Gdl. Now we're going to click porous matrix 1 from underneath the new node that just popped up for porous medium condition. And from epsilon p list, we're going to change this from material to user defined and list the parameter EPS gas GDL. And for kappa under permeability, we're also going to change this to the user defined parameter kappa GDL. Now we're going to add a domain for porous medium and choose anode GDE. And now we're going to add another porous matrix domains. From porous medium 2, we'll again click on the porous matrix subnode and put the user defined porosity and permeability parameters EPS, gas, CL, and kappa CL. All right, and now for wall 1, we're going to click the Show More Options button in the Model Builder window. So that's the little eyeball with the cursor or the little bar over it. And we want to select Advanced Physics option. So if you've already done this in previous tutorials with me, then you'll already have it selected. But if you only have the default GUI set up, then you'll have to show this. Okay, and then we want to go to the Model Builder window under Component 1, Free and Porous Media Flow Anode, and click Wall 1. So this is one of the default conditions we're clicking on. Okay, and then click to expand the Constraint Settings section at the bottom, and from Apply Reaction Terms On list, choose All Physics Symmetric. Right, constraint settings. So the second item is changed from individual dependent variables to all physics symmetric. All right, now for the inlet and outlet boundary conditions, we're going to go to physics, click boundaries, inlet, and for the boundary selection, we're going to choose from the drop-down anode inlet, and we'll change the boundary condition to fully developed flow instead of defined velocity. And then under the fully developed flow section, we're going to define the average velocity as U in anode parameter. The hydrogen coming into the inlet we're saying is fully developed with an average velocity of U in anode, whatever this parameter was set to at the beginning. And that means velocity max for a laminar developed profile would be 2 times the average. And then of course we'd have a no slit boundary at the outside wall. Now for the outlet, we're going to go to boundaries again, select outlets, and from the drop down menu, choose anode outlet. Locate the pressure condition section, and we're going to choose normal flow, selecting that box and leave the suppressed backflow box checked. Okay, now for an added symmetry condition. Again, going to physics, boundaries, selecting symmetry, and we're going to add boundaries 1, 4, 36, and 37, space delimited. Okay, now we're ready for the cathode side. In the Model Builder window, under Component 1, click Free and Porous Media Flow Cathode of P2. In the Settings window for Free and Porous Media, locate the Physical Model section, and from Compressibility list, choose Compressible Flow. We're changing this from incompressible to compressible, which has a Mach number less than 0.3. Define the pressure reference level and the interface properties. So for PREF, once again, we're adding the parameter PREF, even though that is 1 atmosphere, in case we want to change it later. And then we're going to add a porous medium from physics, domains, choose porous medium, and then the domain selection will choose the cathode GDL from the drop-down menu. We'll leave the default option of Darcian flow. You can also choose a non-Darcian model for the porous medium. Next, porous matrix 1. So we're going to click on porous matrix 1 under the cathode porous medium, and change the porosity and permeability to your user-defined and input those parameters we defined earlier, EPS gas, GDL, and kappa GDL. All right, in the physics toolbar, click domains and choose porous medium. So we're just going through the same exercise for the cathode GDE now. And in the settings window for porous matrix, we're going to go to the porous matrix 1. There we go. And again, change these to user defined and put in EPS, gas, CL, and kappa CL. All right, now for the wall. In the model builder window under component 1, free and porous media flow FP2, we're going to click wall 1 and go to the constraint settings and apply reaction terms on all physics symmetric. And then we're going to add another symmetry condition, just like we did on the anodic side. Go to boundaries, select a symmetry condition, and for the boundaries, we'll just go to paste and type in 10, 13, 39, and 40, which will select the outside of the left and right side of the cathode, gas diffusion layer, and gas diffusion electrolyte. Okay, now we need an inlet and outlet for the cathode side. So from the physics toolbar, we're going to choose boundaries inlet and choose the cathode inlet for the boundary selection. Fully developed flow instead of velocity is our boundary condition here. And again, U in cathode is the parameter that defines the average velocity. Then we're going to choose outlet from physics boundaries and choose cathode outlet. Pressure condition is going to be suppressed backflow and normal flow. Now we're ready for global definitions. So let's go back up to the top. I'm going to collapse both of those physics nodes. Use the default model inputs node to set the temperature for the entire model. This node may be accessed by multiple physics nodes. In the model builder window under global definitions, click, so we go to global definitions, default model inputs. So it's the second node at the top here. And then we're going to go to browse model inputs and select general temperature minput.t. and find the expression for remaining selection subsection. And the temperature text field type T. So we're replacing the 293.15 standard temperature with T. So it'll just be the temperature profile that is derived. Right now we're on to the mesh, and we're going to create a mapped 2D mesh in the plane normal to the channel direction, and then sweep the mesh in the channel direction. So for edge 1 in the mesh toolbar, click boundary and choose edge. We're going to select edges 3, 17, 33, 36, 48, and 51. So that'll be the top and bottom of the inlet side. The cathode gas diffusion layer top and the anode gas diffusion layer bottom. All right, and now we're going to right click edge 1 and choose a size. So we're defining a separate size for this specific node. So you'll see a subnode nested under edge 1, and in the element size, we're going to click custom and define the maximum element size as width of the channel 1/8 of the width of the channel. And then we're going to add another edge, boundary edge, and add edges 13 and 65 only. So the left and right side of the cathodic GDL. All right, now we're going to create a distribution, right-clicking edge 2, distribution. And then in the settings, we're going to go to predefined instead of fixed number of elements. And for number of elements, type 8. And the element ratio, type 4. Right, now we're going to add a third edge. So we're just going to duplicate edge 2 this time. Right-click edge 2 and hit duplicate. And then for the edge selection, we're going to clear 13 and 65 and select edges 1 and 57. So the left and right side of the anode side gas diffusion layer. And then again, we'll add, or we don't have to add a distribution because we copied edge 2. So we'll just expand edge 3, go to distribution, and reverse direction for the, just selecting the checkbox for reverse direction. Then we're going to add a fourth edge, and edges 4 and 59 will be the selection. So this tiny section here, the left and right of the anode side gas diffusion electrode. And for this distribution, so we'll right click, add a distribution, and under the number of elements, we'll type 6. For edge 5, we're going to click boundary, edge 5, and select edges 10 and 63 only. So the left and right of the cathode side gas diffusion electrode. And then we're going to add another distribution. Number of elements is going to be 10 here. Edge 6, we're going to go to boundary, select edge, and put 7 and 61. The left and right of the membrane itself. Add a distribution. And in the number of elements, type 3. Edge 7 is going to be another boundary edge addition, and then for the edge selection we'll type in edges 29, 34, 45, and 49. So the left and right of the bulk flow, or the anode channel and cathode channel. Right click, add distribution. We're using predefined number of elements, and we'll use 8 elements with an element ratio of 2. And select the symmetric distribution checkbox. Now we're going to go to mapped mesh, so boundary, mapped, and select boundaries 2, 5, 8, 11, 14, 23, and 27. So the entire inlet side. Swept in the mesh toolbar, click swept. So that's going to add a node at the same level of hierarchy as all the edges and the mapped mesh. And we're going to right click swept 1, add another size for this node, and in the element size section we'll click custom button, and for the maximum element size we're going to define this as the width of the channel. And build selected. Okay, so I'm going to hit zoom extents so we can see the whole thing. And I'll I'll just widen this box for a second so we can zoom in and look at the mesh. So you can see we've got rectangular elements on all sides in all domains with a finer mesh at the electrodes themselves. So that makes sense because we want a finer resolution of computation where, well, if you've got the membrane here and the gas diffusion layer here, the electrode is where the reaction's actually happening. And if you recall from the background, we're assuming that there's an excess of the reactants, the fuel sources, hydrogen and oxygen on both sides. So this process would be reaction rate limited, not diffusion limited. If we were looking at, say, I don't know, an ammonia fuel source instead of hydrogen fuel source, which you can do, is not as good, but ammonia is more readily available and obviously doesn't have the same problems as hydrogen has with pressurization and storage. So for fuel cell usage, that is commonly something people look at. So let's say you're using ammonia and it decomposes into hydrogen. Well, now you don't have an excess of hydrogen. It's going to be most likely that process would not be reaction rate limited. It would be mass transport limited or diffusion limited, because then you're talking about the decomposition of ammonia, and then the presence of the hydrogen that has decomposed from the ammonia serves to inhibit further decomposition of ammonia. So it will drastically reduce the readiness of available reactant there. So in that case, you might want to create a finer mesh in the gas diffusion layer for the hydrogen side. And then maybe you'd keep these the same and these the same, but then have a less fine mesh on the cathode side and on the membrane. Okay, continuing, we're going to definitions. We're going to add a domain probe for the integral of the electrochemical current density to get a polarization plot automatically during the parametric solver process. You can then use this probe also for creating a polarization curve during post-processing. Alright, so domain probes are very useful. So to get there, we'll go to the Definitions tab at top, right next to Home, and then click on Probes, which is a little barrel with a probe in it, or an arrow in it. And then we're going to select Domain Probe. Right, and in the Settings, locate the Probe Type section. So from the probe types, you can choose average, maximum, minimum, or integral. We'll choose integral here and locate the source selection. And we want to choose anode GDE. So in the expression, we're going to use fc.iv underscore H2 GDE R1 all over width of the channel plus width of the rib times length over 24. And if you're wondering where this came from, since I'm working off a tutorial, obviously I can just type it straight in, but if you were doing this and you didn't know where to find it, there's a couple different ways you can find it. So one way is to go to study, and if you haven't actually run a study, then you'll just go to the show default solver, and it'll just take a second to pull up the default settings, and then you can see all the dependent variables, all the expressions that it will use in the actual code in the background. So just go to solution 1, and then you've got dependent variables 1. So you can see the exact expressions for each of these, like comp1. So component1.fc, which is the second set of letters is always going to be the physics node. So like free and porous media is FP, hydrogen fuel cell is FC. So this FC here is denoting the physics module it's in reference to. So it's sort of nesting each of these objects, if you will. So we've got component 1. Under component 1 is fuel cell. Under fuel cell is phi L. And this would be for electrolyte potential. So that's the default variable assigned. In this case, the expression we're using, fc.iv underscore h2 gde r1, doesn't appear here. So it's not something that's going to be solved for in the default configurations. You can also go under dependent variables too and see that it's not there. So if it doesn't appear in the default configurations, there's other expressions you can use in your probe. So let's go back to my domain probe, and you'll just go to replace expression, and under here are all the available expressions you might want to probe for. So there's built-ins, mathematical. You can just expand these and kind of see what's under each of them. So you can pretty much tell from this, or if you had an idea of what you want to probe, oh, I want to get a current density probe or a polarization plot. Well, then you can go under the, let's say, species H2. It's not under there. Okay, so maybe it's under electrode kinetics. And then you've got electrode reaction source, local current density. And this looks similar, not quite it. Here we go. fc.iv for hydrogen at the gas diffusion electrode. R1 is the local current source. So that's the probe we're using. So if you didn't have the exact syntax memorized, which most people wouldn't, you would just come looking for it under expression, and then you can just double click it and that'll enter it into the expression. In this case, we've added additional terms to the expression. So it's coded one parameter, and then we're dividing it by the width of the channel plus the width of the rib times the length. So dividing it by total area, and then dividing again by a conversion factor, 10,000. Now we're ready to study. Firstly, solve for current distribution initialization, both primary and secondary, in 2 study steps, followed by flow in 2 subsequent study steps. Finally, solve the entire model, including the multiphysics couplings, in the final step, along with an auxiliary sweep to solve for a range of potentials and simulate a polarization plot. So step 1 is current distribution initialization. So we'll click on that node under study 1, and in the physics and variable selection section, we're going to clear the checkboxes for solve for reacting flow, for the hydrogen gas phase, and for the oxygen gas phase, because this is just for current distribution and initialization. Now for current distribution initialization 2, we're going to add study steps. So we'll just go to the study toolbar at the top, click on study steps, and choose other current distribution initialization. So we're adding a we're just going to drag and drop this so it's actually step 2. And then under the study settings section, from current distribution type, we're going to choose secondary. The first step was the primary. And in the table, clear the solve for checkboxes for reacting flow, hydrogen gas flow 1, and hydrogen or oxygen gas phase 1. Okay, and you might be asking, why do I need 2 steps? Shouldn't we only need 1 current distribution initialization. There's more documentation on this in the COMSOL, what is this, third documentation knowledge base. If you look up their electrochemistry studies and study steps, version 5.5, but still relevant. Down under current distribution initialization. So the secondary setting may need to be used for problems where the ohmic drop in the electrolyte is negligible, such as in cathodic protection, mixed potential, or thin wafer deposition with lateral electronic conduction problems. When using a secondary initialization, the initial values settings of the potential values may be crucial for convergence. So in this case, the ohmic drop in the electrolyte is negligible. So it seems like even if you didn't know you needed this, you might try to run the study and then have issues with converging to a solution, and then find that, oh, I need the secondary setting because it's crucial for convergence. So it's just, I guess, one of those things that is part of the learning curve of COMSOL. And this is the good and bad thing about COMSOL. It's so powerful and it can model so many things, but it's also so sensitive. So you might have the 99% solution, but there's one setting that's preventing convergence or, creating a singularity. And you can't figure out what is wrong with the model because it seems like all the boundary conditions are in place, all your initial values and your tolerance and everything is good, and you forgot the secondary setting on your current distribution initialization, or you forgot the checkbox for weak constraints or something. So now we're going to go to stationary 2. So we've already got our stationary study set up here, and now we're going to add another step to it. So in the study toolbar, click study steps and choose stationary. This will add a step 4 for stationary 2. Stationary 1, we're not changing. Stationary 2, we're going to clear the solve for checkboxes for hydrogen fuel cell and for free and porous media flow anode. So this one will only solve for the free and porous media flow of the cathode. And again, we're going to add another stationary step. So this will be stationary 3 in the label. And then under study extensions, we're going to expand this and click on auxiliary sweep. Then we'll click the blue plus button on bottom for add, and use the range operator to create a list of potentials from 0.95 volts to 0.4 volts, using steps of negative 50 millivolts for the first steps and negative 100 millivolts towards the end. So we're going to change the parameter name from length to VCell from the drop-down menu, cell voltage, and we'll add 2 ranges here, which you can do either by just typing it in or clicking on the range button. So then it prompts you for the start 0.95, the step is negative 0.05 volts or 50 millivolts, and stop is 0.85. Okay, and then we want to add another range starting at 0.8. Step is in negative 1.1 volts and stopping at 0.4 volts. Okay, so then we've got 2 ranges here, and hit compute. And once it's done, we'll go through the results. So several default plots are generated. Among them are the plots seen in Figure 4 and Figure 5 that show the hydrogen, oxygen, and water mole fraction distributions. And then we're going to modify the polarization probe plot to reproduce Figure 2. We're going to modify the polarization plot, which is from our domain probe we set up, to reproduce the polarization plot in Figure 2. So while it's finishing up with the computation, let's go back and read through the results and discussions. So figure 2 shows the polarization plot of the cell. So we have cell voltage versus cell average current density. That was our domain probe. And figure 3 shows the ionic current in the z direction at the center of the membrane for 0.4 volts. In the y direction, the current density is lower toward the outlet due to lower reactant concentrations. And in the x direction, the current's density is highest in the region close to the channel where the reactant concentrations are higher, but the current density is reduced towards the very center of the channel. This is due to ohmic drops in the gas diffusion layers. Figure 4 shows the hydrogen and oxygen mole fractions for the same voltage level. The oxygen mole fraction is significantly lower in the porous electrode and toward the end of the flow channel compared to the inlet level. For the anode, the trend is the same, but the hydrogen mole fraction level is more uniform. On this side, you've got a lower concentration in the porous electrode region because remember, you've got both water is appearing on the cathode side as well as a reduction of the reactant, your fuel source oxygen. So there's a twofold reduction or twofold reasons why your oxygen is reducing, whereas on the anodic porous electrode, you've only got one reason it's reducing because the reactant's being consumed. Figure 5 shows the water mole fraction in the cell for the same voltage level. Okay, so here's water level. The mole fraction increased due to water production at the cathode is much larger than the effect of removing hydrogen from the gas stream at the anode for these flow and current levels. All right, so here we go. We've got a completed study. It took 22 minutes and 50 seconds, so not too long. All right, so in the model builder window, under results, we're gonna go to ProPlot 15 node. So at the bottom here, and then click ProPlot 15. In the settings window for 1D plot group, type Polarization Plot in the label text field. Polarization Plot. Okay, and then we're gonna expand title, and from the title type, change from automatic to label, and you'll see the label appears on top of our plot over here. And then in the plot settings, we're going to select the x-axis label checkbox and change the x label to cell average current density in amperes per centimeter squared. So x-axis, instead of volts, we want units of this. Okay. And for the y-axis, we want to label this one cell voltage, volts. And then we want to flip the x and y axes, so we'll mark that checkbox, and then under legend, clear the show legends. And plot. So there you have the polarization plot, which is the benchmark of any fuel cell membrane with cell voltage versus cell average current density. All right, now we're on to reproducing the ionic current plot of figure 3 by creating a cut plane data set. In the results toolbar, we're going to click cut plane. So we'll go to results at the top. Cut plane is this little box with a plane through it. And in the settings, we'll go to plane data and choose XY planes. And in the Z coordinate text field, we're going to type, I'm just going to copy and paste this. It's height of the channel plus height of the gas diffusion layer plus height of the electrode plus height of the membrane over. So it's going straight through the middle of the membrane. And I'm going to click plot, even though that's not in there, just so we can see where it's at. So that's just creating the cut plane itself. Now we're going to create the data set. So we're going to go to Results Toolbar and click 2D Plot Group, which is the square. In the data section from Dataset List, we'll choose Cut Plane 1, and then we're going to create a contour plot. So now we've got the geometry we're using for the data set, we've got the data set itself, and now we're going to create a surface, or now we're going to create a contour plot by right-clicking on 2D Plot Group 16 and selecting Contour. Now we're going to go to Replace Expression, and from the menu choose Component 1, Hydrogen Fuel Cell, Electrolyte Current Density Vector, and then we want the Z component, so FDF, and then we want to select the Z component, FC.LLZ. And by double-clicking, it'll populate the expression here. And we're also going to change the levels section for total levels from 20 to 10. Membrane current density. And click plot. So the electrolyte is a polymer membrane and it's facilitating proton transport. So it makes sense that the electrolyte current density would be lower where there is less reactant, and thus there's less facilitation of proton transport. So it's very obvious why you'd have a reduction in electrolyte current density. In the X direction, that's a little more, this is less obvious in the X direction. So why would it be higher on the outsides than the insides? You'll recall one of the conditions we set was fully developed flow through the channels. So that means you have a maximum velocity through the center of the channel. So it's both moving more quickly at the center of the channel, where you have max velocity, which is 2 times the average velocity, as well as being consumed at the electrode. So a slightly more nuanced reason why it's lower in the middle than on the outside. So in addition to those 2 plots we just made, we've got about 14 default plots. Electrode potential with respect to ground. So we've got the multi-slice here with error volume. So you can check that out. We've got electrolyte potential. We've also got mole fraction for hydrogen with a streamline plot. Do zoom extent so you can see that. That one's actually pretty useful. You can see the flow of the reactant to the electrode. We've got the mole fraction of hydrogen surface plot. So same data, but we've got in streamline and surface. And then we've got the same for oxygen with the mole fraction and streamline and a surface plot. So kind of interesting to zoom in and see almost visualize the reaction kinetics here. Then we have the mole fraction of water and streamline. And then we've got the surface plot for the same water mole fraction. And then you've also got mole fraction of nitrogen, streamline and surface plots. You've got velocity plots for FP and FP2, pressure contour plots. So that's it for this tutorial on high temperature proton exchange membrane fuel cell application. But I think this is really cool because first of all, it allows you to check out the polarization plot for material before going into the lab, because that's such an expensive process. And if you can narrow down what type of experiments you want to do before you even get into, what block copolymers are we going to use, what functionalities are we going to use, if you can just run a quick simulation for the type of membrane with the type of electrical parameters or mechanical parameters that you want to fabricate, it would save you a lot of time and help you to narrow down the type of experiments you want to run. If you enjoy watching these, share it with a friend. Help me get to 1,000 subscribers so I can monetize this channel and make even more content for you guys. I'll see you in my next video. Bye.